Hi, I'm Reyne from the University of Sydney, and I'm going to be talking through sample problem K. As I've done with other examples, the first thing I do is I go through these three tests at the beginning. They're a great tool for ruling out options that we potentially don't want to be looking for later. So we can see from our unsaturation test, negative result. So therefore there are no double or triple bonds present. We can see from the oxidation tests that there is nothing that can be oxidized. It's a negative test as well. So we can rule out alcohols, we can rule out aldehydes. We can see from the carboxylic acid that we can rule out carboxylic acid because there's no positive there, it's a negative, no bubbles formed. So we've ruled out a whole bunch now, really. So we're kind of open to the idea that there may be other functional groups present, but we've ruled out at least those ones that we've tested for. Now, as with other examples, I am going to shift down to the NMR data first. I find that that's a good starting point to kind of get an idea of the general backbone structure. And then we kind of come back to mass spec and IR to try and rationalize what else is there. Now we can see down here in our carbon, we only have two peaks. So two peaks here, I'll label these 1, 1, and 2. And unlike quite a few of the other examples I've looked at so far, there's actually a height difference here. Now, you can't really use this in a quantitative way, but it does suggest to me that perhaps peak 2, there are more of these carbons than there are of peak 1. And we'll be able to confirm that when we then come back to look at, say, the mass spec as well. But we can see that peak 1 is extremely deshielded. It's down past 200, which is a bit confusing because we've ruled out a carboxylic acid and we've ruled out an aldehyde. The only other thing I can think of that may have that kind of effect is potentially a ketone. So a ketone being a carbon double bond oxygen, where the carbon is then attached to two other carbons rather than necessarily having a proton there. If we look at our proton NMR, we can only see the one signal, and I'll label this A. Okay. Now for this peak A, we can see that we have a ratio of 6. So there are 6 protons in this environment, and they also only have a multiplicity of 1. It's a singlet. Now, if we remember our N+1 rule, that suggests that this hydrogen environment, this proton environment, there are no protons next to it. Okay, so I've got a bit of an inkling of where this is going, but we'll come back up to the mass spec and the IR before we propose anything concrete. So at this point, we're going to use the simplest ratio. And we're going to say that let's assume that this height difference is important. Let's assume that there is 1 carbon for peak 1 and that there are 2 carbons for peak 2. It looks roughly twice as much. Often at this stage, you will have times where you just need to trial and error a little bit. So if we say that there is 3 carbons, well, that would account for 36. We can see here that we've got 6 protons. So 6 protons is equal to 6, and we're at 42. Now, at this stage, we kind of have a couple of choices. So we've already seen, though, that peak 1 in our carbon NMR is very deshielded, and that's a strong indication that there's probably an oxygen left. So if we just said, well, hypothetically, let's just try 1 oxygen, 16, that is then going to add up to 58. Now, in other examples, you might have a case where you need to consider a symmetrical structure, and therefore you need to double the number of carbons present to reach there. If we doubled the number of carbons here, we'd actually overshoot the mark. We'd end up with too many, or a mass that is too large. But the addition of 1 oxygen perfectly hits that molecular ion peak, or the mass of the molecular ion that we're looking for. So that, coupled with the very deshielded peak 1 in the carbon NMR, tells me that we probably have a ketone. Now we can confirm this. If we come to our IR, we can see this kind of peak here, which is going to be our carbon-hydrogen stretch. We can see this peak down here, carbon-hydrogen bend. I'm just writing these ones as they're on almost everything. You can kind of disregard the fingerprint region. We don't need to worry about that because it just tends to be messy and not very easy to distinguish. And then we've got this very strong, very sharp peak at about 1650. And the first thing I always think about when I see this is a carbon double bond oxygen, which would further support our proposal that there is a ketone present. All right, so let's come down to here then. So how do we rationalize that we have 6 protons in the same proton environment then? And the way that we can think about that is that our ketone must have those 2 CH3s on either side. So the carbon that's connected to the ketone will have no proton in it, therefore no environment, but also means that the 2 CH3s will have no proton environments next to it, and therefore the singlet for their peak. And also, if we take a different color and draw a dotted line, we can see that that's symmetrical. And because it's symmetrical, those 2 proton environments are equivalent to one another, which is why we see the 1 peak and a ratio of 6. If we want to wrap this up fully, we can then think about giving this a name, and we can call this propan-2-one, but I would also accept propanone just by itself. You don't really need the 2 in this case because there's nowhere else it could be. So propanone or propan-2-one would perfectly be both fine so far as I'm concerned if I was marking. I'll call it there. Thank you.